Right, so we'll get started. Last time we talked about normal subgroups and just did a few more details about those. We talked about normalizers. And then at the end, we talked about the Jordan-Holder program, which is this idea that if you want to sort of classify groups, then, well, first you should classify finite groups. First, you should classify the simple groups, and then you should understand how to put those simple groups together. And I said we were going to do the Sylow theorems today, which are one of the main tools for relating the factorization of the order of a group to its structure that lets you sort of say some things about simple groups and sort of existence and non-existence of simple groups. So we're going to get to that. But first, I want to just do at least one example of a simple group before. It's a non-trivial example. So recall, G is simple if it has no normal subgroups except the identity and itself. So if every normal subgroup, if every proper normal subgroup is identity. And again, the reason this is sort of notion is simple is because if it's not simple, then you can sort of put G in an exact sequence where you have H goes to G mod H. So somehow H is built out of the smaller groups, G mod H and H, if it's not simple. Okay, so someone give me an example of a simple group. So the trivial group is an example, good. At least by the definition I wrote, that's definitely an example. Usually we wouldn't talk about, well, yeah, just like sort of we don't treat one as a prime number, we don't usually treat sort of the trivial group as a simple group, but definitely by the definition I wrote, it satisfies that. Okay, what's another example? Great, so, oh wait, sorry, we got two good answers. So the first answer was Z mod PZ for P prime. Then we also got AN for n greater than or equal to 5. Great, okay, so those are some good answers. There are some other ones it's sort of simple to write down, but these are the main ones we're gonna actually talk about, so that's good. So right, then Z mod PZ for P prime, well, if every subgroup is either, every element has order dividing P, so as soon as you have one element, you either have everything or nothing. So this is simple. And here, when you're an abelian group, so these are actually the only simple abelian groups. Just because in an abelian group, any subgroup is normal. So if you have any non-trivial subgroup at all, then you're not simple. So every subgroup of an abelian group is normal. I mean, maybe there's some, well, if you at least restrict to finite groups, then this is, yeah. Anyway, yeah, you could, yeah. Let me not say anything more than that. This statement is true without anything else. So good. So that's the only simple abelian group. And it's like if you take like z mod p squared, see, right? So it is particularly simple to see for like finite abelian groups because you can just look at the classification, and sort of the classification of finite abelian groups sort of tells you that for any prime that divides the order, you're going to have an element of sort of order equal to that prime. So this is Cauchy's theorem for abelian groups, which is much simpler than Cauchy's theorem for general finite groups. Okay, good. And then this we'll talk about a bunch. So the alternating group for n greater than or equal to 5 is the canonical example of a simple abelian group. And so the alternating group for n less than 5 is not simple. Okay, well, probably for n equals 2, it's simple, I guess. And for n equal 2, it's just the trivial group, and for n equals 3, it has prime order. So for n equals 2 and 3, it is simple, but sort of trivially. Then for n equals 4, it's not simple. And for n equals 5 and on, it is simple. It's simple and non-abelian. Great. Okay, so these are some examples. I want to talk about the alternating group because I don't think I've defined it carefully yet. So let's go ahead and define the alternating group carefully. Right. So I'm going to do it in slightly a funny way, but it'll be using things we've already done. So recall we have Sn injecting into GLN of, I can't remember if I did the complex numbers or the real numbers last time, but let me just do the complex numbers. So just by these permutation matrices, by just permuting the coordinates. And then, so this is a group, injection of groups. So this realizes Sn is a subgroup of GLN C. And then, well, from GLN of C, you have a determinant map to C star. And so then I can sort of restrict determinant to Sn. And what I get is called the sign. And if you think about it, sort of the image of this of sign is contained in plus or minus 1. Well, in fact, it's equals plus or minus 1. I can explain that in a second. And then the alternating group is the kernel of sign. Okay, so this is one way you can define the alternating group. So here's a note. And depending on how you define determinant, this may be cyclic reasoning. So often, like in a very first course on linear algebra, the way you would define determinant is sort of you'd take the sum over all permutations of like adding up the product, so the product along that permutation of all the entries of your matrix times -1 to the sign of the permutation. So that's like one definition, common definition of determinant. And of course, if you use that definition, then you have to sort of define sign in a different way and sort of show sign as well behaved, show the sign function is well behaved a different way in order to deduce that the determinant is well behaved. But hopefully, and I think most likely, you've all seen a different way to define a determinant. So the definition of determinant. So you take GLN, let's see, this acts on C to the N, just by linear, sorry, matrices acting by linear transformations. And so then this actually induces an action, so this is a linear, this isn't just sort of an action of sets, like this respects the linear structure on C to the N. So this is sort of an action, and it's something called a representation. But well, here's no surprise, and these are literally just all, GLN is sort of the endomorphism, the automorphisms of this as a vector space. So it's sort of a linear action. So what that means is GLN also acts on anything you can sort of construct out of C to the N using linear algebra. So in particular, it acts on this nth wedge power. So the nth wedge or exterior power of C to the N. And this is one-dimensional. So this is still a linear action. So you get a map from GLN to C to the sort of linear automorphisms, something like aught sub C. So the linear automorphisms of this one-dimensional vector space. But the linear automorphisms of a one-dimensional vector space are always just C star. Like the only automorphism of a one-dimensional vector space is multiplication by a scalar. And like you might worry, like you might think for a second that this is going to this identification is going to depend on a choice of basis, but it doesn't depend on like what basis you choose for this vector space. Like multiplication by a scalar is still multiplication by the same scalar, no matter what basis you write things down in. So this is, and so this map is called the determinant. And so if you think about that, so this probably doesn't look like what was in your linear algebra textbook, but if you think about it, and all this is saying, like, so fixing a basis for the nth wedge power. So this is a good exercise to think about why this is the exact same thing as fixing a non-zero alternating and linear form on C to the N. And then sort of the determinant. So then, yeah, so now you can pull back this linear form by G. That sort of pull back just means you get a new linear form by sort of pre-composing all of your entries with the action of G. And that multiplies this form by some constant, which is the determinant. And if you think about that again, if you fix a basis, so let me just say, and if you use an E1 wedge, again, this is a basis. The nth wedge power of C to the N. And sort of if you express this in the basis, then you're really just getting sort of the expression in terms of columns. And sort of this sign function. Okay, so this is sort of a useful thing. If you've never thought about this before, so if you've never just sat through and worked out how all these different ways of thinking about determinant are the same, then this is a good exercise to do at some point. I mean, I would add to the list, you should probably also at some point think about like why the absolute value of determinant. You should probably also work out carefully at least once in your life, like why the absolute value of determinant is just the amount, like that volume is scaled by your matrix. Okay, but good. So, and the point is, the point of the side note was that, well, even though if you define determinant one way, this will be a cyclic definition. Actually, the natural way to define determinant is this way, and this didn't use anything about having. So this way doesn't use anything about the sign function in the definition, and it proves the determinant is a homomorphism, and then you can restrict it to Sn. That's the homomorphism. Okay, and so, well, I mean, as a corollary of the definition, you find sort of if sigma is equal to tau1, tau2, all the way through tau m, so tau I are transpositions. So that's just a 2-cycle. E.g., tau I could be 1, 2. But, then the sign of sigma is just the product of the sign the tau i's. But that's just -1 to the m, because tau I sort of swaps 2 coordinates in C to the n. Like sort of the linear transformation you get from this permutation tau I, just sort of swapping the 2 coordinates. Like any transpositions, you're just swapping 2 coordinates. But that's just a reflection. And reflections have determinant -1. Like reflection, and somehow. Okay, and now like we're getting into definitions again, like how you, but reflections have determinant -1, and this is in particular easy to check in this case that it has determinant -1. Okay, so good. But in fact, so I claimed that we'd be able to see that sign factored through not just C star, but actually sort of just plus or minus 1. And that tells you this because, well, the sign of sigma is -1 to the m if it can be written as a product of m transpositions. But I mean, transpositions generate the symmetric group. So every permutation is a product of transpositions. And this also shows that like not only is the image just contained in plus or minus 1, it's really equal to plus or minus 1 because I mean, as soon as n is at least 2, then there is a transposition in Sn. So you get something. Okay, good. So yeah, also the fact that transpositions generate Sn, I mean, this is a pretty simple thing to just show completely by hand. Like first you show n cycles. First, you just show that you can write any n cycles, a product of transpositions. And then sort of you go from there. But it's also, I mean, there's an even stronger statement on your homework this week about sort of a specific set of transpositions generating Sn. I mean, there are other, so you just, I'll say this out loud, like you might have seen other definitions of sign. So like, there's this definition of sign in terms of like the number of inversions. And this is sort of useful to know, but it's also like a good exercise to check that it's the same. So sign of sigma is also equal to -1 to the number of inversions. So what's an inversion? Well, if you have 1, 2, 3, 4, 5, up through n, and there are all these different ways you can write a permutation, but one of them is like just arrows saying where everything goes. then so the number of inversions is just the number of points where two arrows cross. Which you can also write down just a mathematical sentence that says this, but this is sort of the right picture of your head. So it's also a good exercise to check that like this agrees with these other ideas. And we won't need this. Right, and so good. So I guess I should say then the definition is the alternating group is just the kernel of the sign. So this is contained in Sn, and so for n at least 2, so when Sn is not the trivial group, then it has index 2. And for n not 2. So its quotient is just this group plus or minus 1 inside of C star, which is just cyclic of order 2. And so it's normal, and the index is equal to 2. So, and it's also, in another way to write being in the kernel sign is sort of it's the, we call them the even permutations. You can say they're even because their sign is 1, not minus 1. So the number of versions is even. Or I think where the term, I don't know, actually, I don't actually know where the terminology even or odd comes from, but I mean, it's the way I usually think of it in my head is it's, so saying you're an even permutation means when you express it as a product of transpositions, there's always an even number of transpositions. So that follows sort of from this formula, which is sort of interesting when you think about it, because I mean, there are many, like any permutation can be written as a product of transpositions in many different ways, like with many different, like, sort of different numbers possible of transpositions. So there's no guarantee there's going to be sort of any sort of invariance, but it turns, and sort of the existence of sign is sort of exactly telling you that there is some parity control over the number of transpositions. Like any permutation, well, you might be able to write it as product of 2 transpositions or 4 transpositions or 6 transpositions, but if you're able to write it as an even number of transpositions, as a product of an even number of transpositions, then you definitely can't write it as an odd number of transpositions. So this is sort of some invariance in writing. So if written as a product of transpositions, there are an even number. Okay, so that's the alternating group, AN. It's a subgroup of Sn. And going back to the start, it's going to be a simple group for n greater than or equal to 5. So that's one of the things. That's one of the things we'll show. Not this week. I guess hopefully we'll show it on Tuesday, or at least discuss it on Tuesday. Good, but before that, and before we do the Sylow theorems, let's do at least one case of it. So let's show that the alternating group is simple for n equals to 5. So for that. So we'll show AN is simple for, or we'll show A5 is simple by a counting argument. Okay, so how can we make a counting argument here? Well, we use 2 facts. So one, we already discussed this. We discussed this last time, but any normal subgroup is a union of conjugacy classes. Because I mean, just from like the simplest definition of a normal subgroup, it's sort of preserved under conjugation by any element. That means like if you start with something in your normal subgroup and you conjugate it, like that's still in your normal subgroup. So you contain that normal subgroup has to contain the whole conjugacy class. So this was one of the equivalent definitions of a normal subgroup, was that it was a union of conjugacy classes. So that's the first fact we'll use. And then the second is just Lagrange's theorem. So the order divides the order of A5, which is the order of S5 divided by 2. And so I think you've all at least done this on the homework, even if you didn't know before. So this has certainly come up in solving some of the problems if you've solved them all. So the order of S5 is 5 factorial. The order of Sn is n factorial. And so 5 factorial over 2 is 120 over 2, so that's 60. Okay, so we know the order divides the order of A5, and we know it's a union of conjugacy classes. So you just have to sort of check that no union of conjugacy classes, no possible union has as the order dividing that of A5. And so I'm not going to, so what are the orders? I'm not going to do it completely, but because related computations are in your homework, but so the conjugacy classes have size is let's see. The conjugacy classes have sizes 1, 12, 12, 15, and 20. So these are, this is the trivial conjugacy class. This is the conjugacy class of a product of 2 transpositions. This is the conjugacy class of 3 cycle, and sort of these are both conjugacy classes of 5 cycles. And we know the conjugacy classes in the symmetric group are determined by the cycle type. But these are not conjugacy classes in the symmetric group. These are conjugacy classes in the alternating group. The alternating group is a normal subgroup of the symmetric group. So the alternating group is a union of conjugacy classes in the symmetric group. But some of those conjugacy classes can break up. So here we see that in this case, it just happens for the 5 cycles. So the 5 cycles, which are one conjugacy class in the symmetric group, become 2 distinct conjugacy classes, even of different sizes, in the alternating group. As long as I didn't screw anything up. Okay, anyway. And the main point here, just that conjugacy classes the main point is that the conjugacy classes can split up. Like a conjugacy class in Sn, like if you have an even conjugacy class in Sn, so a conjugacy class consisting of even permutations, which just means which is completely determined by the cycle type, then sometimes it can split into multiple conjugacy classes in the alternating group. And this is the case where it does. And so one of the homework problems is to one of the problems, not exercises on the homework this week, is to investigate this phenomenon and figure out exactly when this happens. That's why I'm not going to say anything more about this, because this is sort of a first case you can investigate if you want to do that problem. Okay, so and if not, it's easy to verify by hand anyway. In this case, and do those add up to 60? Yes, those add up to 60. Good. So good. But now we can just check. So now you just try to add these up and get a divisor. And well, you can't. You might say, well, a divisor of 60. Well, you can get 1. 1 is a divisor of 60, but that's the trivial subgroup, and you can get 60, but that's the whole thing. So you want to get sort of a non-trivial divisor. But well, you can just do them all by hand. You might say, oh, 20 is a divisor of 60, but you always, and it's a subgroup, so always has to contain 1. So sort of, and this is an argument you can sort of try and make more like not just for A5, but for other groups, like this is an argument that you can sort of sometimes make to show a group is simple. It can certainly, it certainly cuts down the number of computations you have to do to like show a group is simple. And in this case, you can really sort of finish and show so that you can't do this, so the group is simple. So, and if you can't add these together to get a proper divisor of 60, then there's no way you can get a normal subgroup. And if you can add them together to get a divisor of 60, that doesn't mean those form a normal subgroup because they might not be a subgroup. But if they are a subgroup, then they'll be normal. Okay, and now I'm just checking my math to make sure that's accurate. But yeah, it really looks like you can't add these together in any way to get a divisor of 60. Okay, so yeah, so that's our first example of a simple, sort of first non-abelian example of a simple group. Okay. So let's go ahead. I'm going to state the Sylow theorems, and then we'll take a break. I guess I have to make a definition. So a P group is a group of order a power of P. So here P is a prime number. And so then if H is contained in G, is a P subgroup if, well, it's a P group. And it's a Sylow subgroup if well, let me say it this way. If it's a P subgroup, so its order is a power of P, and sort of its order is like the maximal, like the largest numerically possible. So that means that the index of G and H is not divisible by P. Okay, so another way to say this is if sort of G is equal to P to the A times K, where P and K are co-prime, or just P doesn't divide K, I guess, then H is a Sylow subgroup. If the order of H is equal to P to the A. Okay, so then what's the theorem? Okay, well, I'll say in a second, but let me just point out, from the definition, there's no reason these should exist. Like, it's not clear at all from the definition that there should be a Sylow subgroup. Like, just nothing we've done so far tells us that you're going to have, like, this really requires proof to even see there's a Sylow subgroup. Like, nothing we've done so far tells us there has to be a group of this order. Like, we know that if you have a subgroup, its order divides the order of the group, but we don't know anything about like which orders of the group, like which divisors of the order sort of actually have subgroups of that. So we haven't discussed that converse problem essentially at all. Okay, and so good. So the theorem is so if G is a finite group, then 1, G has a Sylow subgroup and moreover, they are all conjugate. So not only is there a Sylow subgroup, so a group of this sort of largest possible prime power, a subgroup of this largest possible prime power order, but any two of those subgroups are conjugate, which is again, like, definitely not automatic. Like, a general group can have sort of many different subgroups of the same order that are not conjugate. But you just think, like, for example, in the symmetric group, if you look at like a 2-cycle or like a product of two distinct 2-cycles, sorry, a product of like two distinct non-overlapping 2-cycles, like both of those have order 2. So like they're both copies of Z mod 2Z in there, but they're definitely not conjugate. Like, so there's no reason for sort of two subgroups of the same order to be conjugate in general. Moreover, and we can add this part that they're all conjugate can actually be strengthened. So this is a strengthening of the second part. If H is contained in G, then, well, I guess you can state it as a strengthening. I'll just, since I've stated it this way, I'll state it just as an extra property. So if you have a P subgroup, then so if H is a P subgroup, then it is contained in a Sylow subgroup. And it really should be a Sylow P subgroup. Sorry, I should have said that everywhere up here, because of course this depends on P. And okay, so sorry, that was what I said before was a little bit confusing when I started writing the second statement. That's all I meant to say was, so it's possible to rewrite sort of the end of this first statement and the second statement together as one statement by saying, like, sort of fix a Sylow subgroup, P subgroup, then any P subgroup is sort of contained in the conjugate of that one. And I think maybe if you look in like Dummett and Foote, that's how it's written. But for me, somehow it's conceptually easier to split them out like this. And then 3, if NP denotes the number of Sylow P subgroups, then NP, well, so one part's easy. NP divides the order of G. Sorry, and so it divides the order of G, but it divides the order of K, where sort of G is P to the A times K, just above, P not dividing K. So it divides sort of the co-prime part of the order. And its NP is congruent to 1 mod P. So yeah, and again, it's a question of how you want to write it. If I know that NP is congruent to 1 mod P, then if it divides the order of G, like it has to just, like it's also co-prime to P, so it sort of has to divide sort of the prime to P part. So here it would have been, this is a little bit redundant, like I could have just write NP divides the order of G, and NP is congruent to 1 mod P. Because sort of as soon as NP is congruent to 1 mod P, like definitely sort of divides the order of G, it divides sort of the co-prime to P part. But it's somehow useful when you're using this to just have it remembered like this. Okay, so and this is an incredibly strong structural theorem because it goes from just, and again, like it just goes from the simple numerics, like the factorization of your group, to telling you some very strong properties that your group has to have, like some very strong statements about what subgroups have to exist in your group. And so let me just like give you the main observation. So why is this like useful for studying normal subgroups? Well, the theorem implies that a Sylow P subgroup is normal if and only if, well, NP is equal to 1. So the only way you can get a normal subgroup, Sylow P subgroup, is if the number of them is equal to 1, because, well, all of the Sylow P subgroups are conjugate to each other. And so, I mean, if there's more than one of them, then there's some conjugate, there's a way to conjugate one to another one. So, so it can't be normal. So this is the only way you can be normal. But then you have sort of some numerical control over this. So now you get some control over this number by part 3. So yeah, so we'll do an example. We'll do an example here. So why don't we take, how is it? Let's take a 10-minute break. So we'll take a 10-minute break. Then we'll come back. We'll do an example of sort of how you can use this to sort of prove some, like how you actually sort of use this in an argument, and then we'll start proving this theorem. Yeah, sure. Yes, thank you. That was, yeah, everywhere. Yeah, thank you. If I did that elsewhere, yeah, sorry about that. That was always supposed to be order. Thanks, Thomas. Okay, so we'll resume at 1:20. Okay, so we'll get started again. Before we go back to the Sylow theorems, I just wanted to correct my labeling of the conjugacy classes from earlier. Sorry. I went back and checked this because I was disturbed by something. I was correctly disturbed. So good. Oops. There goes that. Now I've erased this somehow. Highlighter. There we go. So the two conjugacy classes of 5 cycles should be the ones of size 12. And so they should split into sort of 2 conjugacy classes of the same size. It shouldn't be. Yeah. And there's a reason that you don't get different size conjugacy classes here. And so as the 15 was sort of the product of 2 cycles, and the 20 was a 3 cycle. Okay, yeah, so sorry about that. And oh, I added sort of note, and if you want to see this verified, you can also find this on page 127 of Dumb and Foot. This is an example there. Okay, good. So going back to Sylow's theorem. Okay, so let's do an example. Before we prove it, we'll do an example of how you use this. So there are no, and there are simpler examples of how you can use this, but this is sort of a fun example. This was on the quals in May, so it's not gonna be on the quals again here. And it's not gonna be on the quals again this semester. So there are no normal subgroups of order 448, which is 2 to the 6 times 7. Okay, so why? Let's see, so let's look at N2. So number of Sylow 2 subgroups. So these are subgroups of order 2 to the 6. So yeah, let's suppose we do have a G. This doesn't make any sense. Sorry, there are no simple groups of order 448. So I'm going to, yeah, I don't know. Sorry, I don't know how I wrote it the way I wrote it. That was just nonsense. There are no simple groups of order 448. So what do we have to do? We have to sort of take a group of order 448, and we have to produce a Sylow. We have to produce a normal subgroup. So suppose the order of G is equal to 448. Okay, well, let's just, for this kind of problem, like what you do is you first, when you have the factorization, so you just sort of compute like what are the possibilities for NP. So we know we can have, so let's do them out. So N7, this divides 448, and it's congruent to 1 mod 7, or yeah, 1 mod 7. So it can be, well, sorry, it divides 448, but it divides it divides 2 to the 6, and it's congruent to 1 mod 7. So we could have N7 is equal to, well, it could be 1. That would be good, because that would, if we could somehow conclude that N7 had to be 1, then we'd be in good shape, because then we'd know that there was a normal subgroup. Because as soon as you show like one of these MPs is equal to 1, that Sylow subgroup is a normal subgroup. That means there's just one Sylow subgroup and it's a normal subgroup. But that's not the only possibility for N7, because if I take 2 cubed, that's 8, which is also congruent to 1 mod 7, and still divides 2 to 6. So I could have 8. And similarly, I could also have and 2 to the 6 itself, which is 32. No, 2 to 6 is 16, 32, 64. 2 to 6 is 64. Sorry. These are all 1 mod 7, and they all divide 2 to 6. Okay, so, well, turns out this is a dead end for this proof. Like it's possible that N7 is equal to 1, but also it's possible there are many Sylow 7 subgroups that are conjugate, and then sort of, there's no way to deduce. Well, we'll see. Let's try 2 and see what happens at 2, and you'll see sort of what we do at 2 will let us sort of conclude, and then you'll sort of see why it wasn't going to work with 7. Okay, let's do N2. So N2 divides the number of 2 Sylow subgroups, divides 7. That's good, it's a smaller number. And N2 is congruent to 1 mod 2. So this is no information. So and this is sort of an annoying part about 2 Sylow subgroups is this, and for other primes, like this conjugacy condition is sort of pretty strong. Like being congruent to 1 mod 7 cuts out a lot of options here. Like we eliminated a lot of options here. Then being congruent to 1 mod 2, when you already know you're odd, like that's not new information. So this is not new information. But okay, but we know N2 divides 7. So we know there's either equal to 1, N2 is equal to 1, or N2 is equal to or n2 is equal to 7. Okay, so if n2 equals 1, then the Sylow 2 subgroup is normal. That's exactly, so n2 equals 1 means there's a unique Sylow 2 subgroup, right? Sort of any conjugate of a Sylow 2 subgroup is a Sylow 2 subgroup. So that means any conjugate has to be this single one, and so it's normal. This is just what I was saying up here. A Sylow P subgroup is normal if and only if n equals 1. Okay, so if n2 is equal to 1, then we're normal. There's nothing that's telling us n2 has to be equal to 1, though. So it is possible that n2 is equal to 7, at least a priori. And probably, I didn't work out actual examples of groups of this order, but probably a posteriori as well. So if n2 is equal to 7, then well, we can look at the action of G by conjugation on this set of Sylow 2 subgroups. Okay, so that means we get a map from G to S7. So size of the set, 7 elements. And because we know this action is not trivial, this is not a trivial action. Because we know all the groups are conjugate because it's transitive. So this is a conjugation action on the Sylow 2 subgroups. We know there are 7 of them. We're saying we're in the case n2 is equal to 7. And the Sylow theorems tell us all of the Sylow P subgroups are conjugate. So that says that whenever you take the set of Sylow P subgroups and you look at the action of G on it by conjugation, that's a transitive action. So, okay, so this map, so, and where are we going to get a normal subgroup out of it? So our normal subgroup is going to be the kernel of G. And the fact that the action is not the kernel, sorry, let me call this map phi, this action map. This kernel phi is normal in here. And the fact that the action is non-trivial tells you that the kernel of this is not G. There's something that acts non-trivially. We then have to deduce that the action is not faithful. So we also need to know that the action is so that this kernel is not empty. Or not just any element. Because then it's a non-trivial normal subgroup. That's our game. We're trying to sort of show that there's some non-trivial normal subgroup. Well, then I can look at the following. I mean, I have, so if the kernel of phi is equal to E, then phi is an injection from G to S7. And that means I can think of G as being a subgroup of this permutation group. That means the order of G divides the order of S7, which is 7 factorial. This is 2 to the 6 times 7. Okay, but well, what is 7 factorial but 7 times 6 times 5 times 4 times 3 times 2 times 1? And if you think about powers of 2 here, you have a 2 from the 6, a 2 from 2 2s from the 4, and a 2 from the 2. So you have 2 to the 4 times 7 times 3 times 5 times 3 times 2 times 1, or times 1, sorry. So I just sort of took all of the 2's out, 6, 4, and 2. This is where I got all my 2's in my factorization. And, well, that's my contradiction, because 2 to the 6 does not divide 2 to the 4. So that means the kernel is not just the trivial group. But we already saw the kernel is not the whole thing. So the kernel is a non-trivial normal subgroup. And again, G is not simple. So this is sort of, and this is a good trick to remember. So there's one of the problems on your homework assignment this week is just like 5 problems that are just like this. Sort of, and this is basically, and this is how you use the Sylow theorem to like prove something is not, like there's no simple group of some order. Like first you like, well, and first you can see what you can do just by sort of counting. Like, can you like force one of these MP to be equal 1? And there are some cases where you can just immediately force one of these MPs to be equal to 1, just sort of based on conditions. And then if you can't, like you look at, instead you sort of look at one of the like the actions you get on the Sylow P subgroups by conjugation, and you sort of try and sort of use that action to get something else. Yeah, and it's kind of sort of an amazing way you can get structure out of nothing by using this. Like I think this is a nice example of the way sort of mathematics structures things that don't appear structured. Okay, anyway, that's sort of a good example of how you use the Sylow, like how you can use the Sylow theorems. Okay, so now we should talk about proof. Okay, so let's see, we have 10 minutes, so let's show existence. And then we'll come back on Tuesday to show the rest. Okay, so we're going to argue by induction. On the order of the group. Okay. So our base case, well, so the base case that we're gonna want to induct off is when the order is just a prime number. So yeah, and you could also do the induction. Yeah, no, we should do it this way. So the order of G, so base case. Well, but then G is equal to Z mod PZ. Because any non-trivial element has order P. And so is the full group. So then, and G is itself a Sylow P subgroup. Okay, so now we need to do the inductive step. Okay, and so what we're going to do is we're going to show, yeah, we're going to use the class equation. So Okay, so how are we going to use the class equation? Well, let me write G is equal to P to the A times K, just so I have that. So I'm going to fix representatives. G1 is through, I'll call it GM for the conjugacy classes, the non-central conjugacy classes. And then I get that the order of G is equal to the size of the center times, sorry, not times, plus the sum over from I equals 1 to M, so all these other conjugacy classes of, well, the size of that conjugacy class, the size of the conjugacy class is just by the orbit stabilizer, it's the index of the centralizer of G of GI. Okay. So I'm going to break up into two steps. So I'm either going to apply induction to one of these centralizers, or I'm going to use the center. So here's the idea. I mean, well, suppose P doesn't divide this index for some I. So suppose there's some I where P doesn't divide this index. Then, well, the order of CG, GI, is equal to the order of G divided by this index. But since this index isn't divisible by P, like it's going to be sort of P to the A times some other number L. And because this conjugacy class is non-central, like this index is non-zero. So this is definitely going to be smaller than the order of G. So I get a subgroup whose size is smaller than the order, like I get a subgroup of smaller size, but where the same power of P is dividing it. And so by the inductive step, the inductive hypothesis implies that the centralizer has a normal subgroup, or has a Sylow P subgroup. So thus so does G, because a Sylow P subgroup of the centralizer is just a subgroup of order P to the A, but a subgroup of order P to the A in here is also a subgroup of order P to the A in G, which is a Sylow P subgroup of G. So, okay, so if P divides the order, if P doesn't divide any one of these orders, then we're done. On the other hand, so if P divides all these orders, for all I, well then, since P divides the order of G, I guess, and I wasn't being very careful. And let me assume A is greater than or equal to 1 here. Of course, if P doesn't divide the order of the group at all, then there's a Sylow P subgroup, which is the trivial group. So let me assume A is greater than 1 here. So, okay, so P divides all of these centralizers, and P divides all these indices, and P divides the order of G. Well, for this equation to hold, P also has to divide the order of the center. So P divides the order of ZG. Okay, and so that means, yeah, so how to, so maybe let me just, 3 minutes left. Let me say the rest as just an exercise, because I think I got confused about, I think I'm going to screw up the argument in the next part, and we only have 3 minutes, so I won't recover. So let me just say outline how you do the rest, and then I'll leave it as an exercise for all of us to do before class next time. So now, okay, so P divides the order of ZG. We have G mod ZG. So I can take the quote. So the center is always normal. Oh, I see what I should do. Sorry. Got it. Okay, I'll do it right since I remembered how to do it now. Okay, so P divides the order of ZG. So ZG is abelian. Is a finite abelian group. So it contains a subgroup of order P. Let me call it H. So just any finite abelian group, just by the classification, contains an element of order P. Okay, well, so H is a normal subgroup of G, because any subgroup of the center is a normal subgroup of order P. Okay, and so I can look at H, just the G, and then I take the quotient G mod H. Now the order of G mod H is less than the order of G, so it's equal to P to the A minus 1 times K, which is less than the order of G. And so, so it has a Sylow P subgroup. So I'm going to run out of letters. Let me call it capital M. Let me call this projection, so this quotient map pi. And then pi inverse of M is a subgroup of G. So every time you have a map of groups, if you sort of take the preimage of a subgroup, that's still a subgroup. And because this map pi is surjective, you can check that the order of the preimage of M is just the order of the kernel times the order of M. And that's P times P to the A minus 1, which equal to P to the A. Okay, so that concludes the proof of existence. So this was just part 1 of the theorem, if I remember right. It's not even all of part 1. So part of 1. But this is actually, and this is the main thing in the proof is to see that they exist. And then after you see that they exist, the other arguments are not, the other parts. So there's one other clever trick, and then sort of the other parts of the Sylow theorem sort of fall in order. Okay, good. So we've finished proving that Sylow P subgroups exist, and next time we'll finish proving the Sylow theorems. I'll stop there, and but I'll stick around for a few minutes if anyone has questions.